Jakub Konieczny. He's currently at the University of Oxford, and he'll be speaking to us about arithmetical subword complexity of automatic sequences.
Thank you so much for the introduction. Thanks so much for the invitation. I will indeed be talking about arithmetical subword complexity of automatic sequences. This can be construed as a second part of a two-part series, which was started 2 weeks ago by Clarence Molnar. So there will be quite a few connections. I have tried to keep the talk self-contained, so there will be a little repetition. And if you haven't been to the talk 2 weeks ago, then you don't need to worry. Okay, so let's get started. Most fundamentally, what I'm going to be talking about is complexity of sequences. So the basic question that you could ask is, well, given a sequence A, taking values in some finite alphabet omega, maybe just a two-letter alphabet 0, 1, how complex is this sequence? Now, at this level of generality, this is, of course, quite a pointless question. It's too vague to be answered, but there are several things that you could look at in this general space. For instance, you could try to consider the computational complexity of finding AFN, which is something that people have looked at, but we're going to focus on things that are a bit more concrete and a bit more accessible. Perhaps the most classical notion of complexity is subword complexity. So subword complexity is the function which I'm going to denote by P A of L, which just counts for each integer L, how many length L subwords you can find in A as a continuous segment. So here's a formal definition if you want. Now, a slightly different but closely related notion is arithmetical subword complexity. It was introduced relatively recently by several authors whose names I would surely mispronounce, so I'm not going to try. And it counts the number of length L subwords that appear in our sequence, but not as a continuous segment, but instead as along an arithmetic progression. So here's again a formal definition if you want. And these are by no means an exhaustive list. There's also polynomial subword complexity, V complexity, pattern complexity, asymptotic subword complexity, and you can expand the list as far as you want. I will mostly not discuss those, except for polynomial subword complexity, which will make an appearance. Now, subword complexity is very classical and very well studied, so let me just give you a quick reminder of the theory. So we have trivial bounds. In one direction, you can have there's at least one subword, and from above, there's at most as many subwords as there are words of length L over the alphabet. And both of those can, of course, happen. The subword complexity is most interesting in the regime where it's small. And in fact, we have a very good understanding of what happens then. If we have an eventually periodic sequence, then the subword complexity is bounded. And conversely, if you can find at least one value L such that the subword complexity at L is at most L, then the sequence has to be eventually periodic. This means that the least possible subword complexity is linear, and more specifically, it's L plus 1. And this is realized for Sturmian sequences. Sturmian sequences are sequences given by this particular formula. You can define them also in several other ways. And this is an even on the state. Next, what we're really interested in are automatic sequences. These sequences have a very notable property of having subword complexity that's almost as low as possible. So their subword complexity is linear, meaning that it's bounded by C times L for a certain constant C. Now, just in case you're not very familiar with automatic sequences, let me give you a very quick introduction. And in fact, let me start with the most famous automatic sequence, which is the 2-Morse sequence originally discovered by Pruitt. So this is the sequence. I'm going to write it as a plus minus one value sequence. Here are some initial terms, and there are several ways to define it. The most explicit way is to just say that it's plus or minus one, depending on the parity of the sum of digits. It's computed by the automaton in the picture here. It's given by a recurrence formula, which just defines t of 2n and t of 2n plus 1 in terms of lower values. It's a fixed point of a substitution, meaning that you start with a plus 1, then you change every plus 1 to plus 1 minus 1, and every minus 1 to minus 1 plus 1. You keep iterating those operations, and in the limit, you obtain the 2-Morse sequence. And it's also a strongly two multiplicative sequence, meaning that if you have an integer and you split up the digits into 2 blocks, then the value of 2-Morse at this integer is the product of the values at those 2 blocks. Now, to be more precise, let me properly define what's an automatic, what I mean by finite automata and how we exactly define automatic sequences. So we're going to need a little bit of notation. I'm going to let sigma k denote the set of digits base k, so it's just integers from 0 to k minus 1. I'm going to use sigma k star to denote the set of words over sigma k. For an integer n by n in round brackets, I'm going to denote the base k expansion, and for a string of digits w, and by w in square brackets, I'm going to denote the integer encoded by w. Now, an automaton consists of a finite set of states, a transition function which takes a state and a digit and outputs a state, and an output function which takes a state and produces some output. So if we have an automaton, we can use it to compute a sequence by first extending the transition function to take strings of digits. And here there's 2 ways to do that. You can say that if you are in state S and you read input uv, then you first follow the path encoded by u, and then you follow the path encoded by v. Or you can say that you first follow the path encoded by v, and then the path encoded by u. One of those will correspond to reading the input starting with the most significant digit, and the other one will correspond to reading starting with the least significant digit. And now, to compute the nth term of a sequence, you first write the base k expansion of n, then you follow the path in the automaton encoded by this sequence of digits, and at the state which you reach, you read out the output. So, for instance, the automaton above computes the second most famous automatic sequence, which is the Rudin-Shapiro sequence, which counts the parity of the number of pairs of consecutive ones in the binary expansion of n. Now, in case you're not familiar with automatic sequences, it's for the most of the time, it's going to be quite enough to remember that automatic sequence is something that's computable by a finite device. And in fact, if you can think of another notion of a computable by finite device, it's almost certainly going to be equivalent to the definition that I just gave. Okay, so let's move on to subword complexity of automatic sequences. In many cases, you can compute it very explicitly. For instance, the complexity of the 2-Morse is given by this slightly clunky formula over here. It doesn't matter exactly what the formula says. It's just something that we can compute. And as a general rule, like I mentioned, the subword complexity is at most linear. And in fact, this is a very simple fact. So let me just quickly sketch out a proof for you. So first of all, let's start with the observation that if you have some integer of the form k to alpha n times n plus I, where I is less than k to alpha, then the value of the sequence is fully determined by, first of all, what the automaton does if you give it n as input, well, and then of course I. So this means that if you're trying to count all the words of length, say k to alpha, that appear in our sequence A, then, well, any such word appears at some position k to alpha n plus r. It ends, well, at where it has to end. So in this situation, this word is going to be fully determined by what the automaton does on input n, what it does on input n plus 1, and on the position where the word appears r. So at the end of the day, the complexity is going to be at both the number of states squared times k to alpha. So that gives you the claim if length is a power of k, and in the other case, just use monotonicity. Okay, so ultimately, we are interested in the complexity of sequences along arithmetic progressions. So let me talk a bit about complexity of arithmetic sequences along subsequences, and let's start with 2-MOs. This is also something that Clemens discussed quite a bit. Now, the general intuition is that if we have a sequence, say, let's call it an n, which does not have too much to do with binary expressions, then applying 2-MOs to the sequence should produce a result that looks fairly random. So in particular, we expect that plus and minus ones should appear with approximately the same frequency, meaning that the average value is going to vanish in the limit. In fact, we expect that it should be normal, meaning that the correlations should vanish in the limit. And as a consequence of normality, we would expect that it should have maximal subword complexity. So the subword complexity should be 2 to n. And this expectation was indeed confirmed in several cases. The Motamedwi and Rivar showed that the 2-MOs along the squares is normal, which in particular implies that it has maximal subword complexity, 2 to n. And the same result was proved for 2-MOs along Kwiatkowski-Shapiro sequences, by which I mean sequences of the form n to some non-integer power c, where we need the c to be between 1 and 3/2. I think that's the best published result, but it can quite certainly be extended. So coming back to arithmetic sequences, it would be nice if we could just say the 2-MOs along some arithmetic progression looks uniform and hence has and hence any word is going to appear. But this is very much not the case. If we restrict to an arithmetic progression, then we again get an automatic sequence. So in particular, something that looks very non-random. However, what we hope, and this hope is going to be realized very shortly, is that if we restrict to a random arithmetic progression, then the result is going to look random. Now, let me try to make that a bit more precise. And in order to do that, we're going to need a little bit of so-called higher order Fourier analysis. So the main object of study in higher order Fourier analysis is Gauer's norms. Now, for each d, we have the Gauer's norm ud, and this norm is defined for sequences that go from some initial interval of integers of length n to, let's say, the complex numbers. And it's defined as follows. We consider all d plus 1 dimensional parallelepipeds contained in our interval. We compute the value of f at each of the vertices of those parallelepipeds. We apply the complex conjugate to every second vertex. We multiply this all together. We take the average over all possible parallelepipeds, and then we take 2 to the root in order to make it homogeneous. Now, this might look like a somewhat something of a strange formula to be looking at, but it turns out to be useful in additive combinatorics, largely because of the so-called generalized von Neumann theorem, which is the following assertion. So let's suppose that we have d plus 1 functions on the initial interval of length n, and we're interested in compute the average, where we average over all arithmetic progressions contained in the first n integers, and on the ith term of the arithmetic progression, we apply fi, and we take the product of all of those. So we're looking at an average that looks like so. And it turns out that Gauss norm can control those averages. Specifically, this average is bounded by a constant times the smallest of the Gauss norms of the sequences involved. As an almost immediate corollary of this result, we conclude that if we have a sequence f that takes values, let's say plus and minus 1, and that has small d plus 1, it should be small ud norm, then it's going to look random along d plus 1 arithmetic progressions, in the sense that if we compare the number of d-term arithmetic progressions where we see a specific factor and normalize it by the number of all arithmetic progressions, then the result is going to be what we would expect for a random sequence of plus and minus ones. So 1 over 2 to d plus 1, plus an error that's at most of size epsilon. So in particular, this means that if we have a sequence that's Gauss uniform in the sense that each ud norm tends to 0 as n tends to infinity, then the sequence is going to have maximal arithmetic subword complexity. And some time ago, I was able to show that 2m Morse is Gauss uniform of all others. In fact, you can get somewhat more precise bounds, where the ud norm for each d tends to 0 like a negative power of n. And this in particular has the consequence that 2m Morse has maximal arithmetical subword complexity 2 to n. That second observation is by no means new. It has been, in fact, discovered several times by different authors. Now, the result from the previous slide suggests that if we're interested in arithmetical subword complexity, then uniform sequences are good for us. So let's see which sequences are Gauss uniform. And this is something that we've been able to characterize together with Kuba Wyszewski and Klemens Boyer. It turns out that in order for an automatic sequence to be uniform of all orders, it's enough that it's uniform of order 2. And for this, it's enough that its averages along any arithmetic progression tend to 0. So intuitively, this means that the U2 norm doesn't, in general, have to be small. Automatic sequences can have some sort of structure that's picked up by the U2 norm. This is somehow a linear structure, but it cannot have a structure of higher order. It cannot have quadratic, it cannot have cubic structure. So from here, we immediately obtain a fairly broad criterion for an automatic sequence to have maximal subword complexity. Indeed, it is enough that our sequence takes two values, let's say 0 and 1, and that there exists some constant alpha such that along every arithmetic progression, the averages of A tend to alpha. And the idea behind the proof is quite simple, really. We just notice that by the criterion above, if we subtract from A the constant function alpha, then the resulting sequence is going to be Gauss uniform of all orders. And then if you just try to compute all frequencies of subwords that appear along arithmetic progressions, you're going to get a result that's almost the same as if we had a random sequence where ones appear with frequency alpha. Now, unfortunately, not all sequences are uniform, and these are sequences which might give us a little bit of trouble. So let's see some examples of sequences that are not uniform. Specifically, we have periodic sequences, let's say alternating plus ones and minus ones. Next, we have forward synchronizing sequences, which include examples such as -1 to the largest power of n of 2 that divides n. It's a sequence that's almost periodic in the sense that it's very well approximable by sequences with periods that are powers of 2, but it is not exactly periodic. And another class of examples is backward synchronizing sequences. And these are sequences such as -1 to the length of binary expansion of n. And this sequence is going to look constant on very long intervals, but depending on which interval you look at, is going to be plus or minus 1. Now, let me formally define what I mean by synchronizing. So first of all, a synchronizing automaton is an automaton which has a synchronizing word, which is a word W such that there is a state S, such that whenever we follow a path encoded by W from some other state S prime, we always end up in S. So somehow, if your automaton is doing any sort of computation and you feed it output W, you can know where it's gonna, in which state it's going to land. And now I'm going to say that a sequence is forward synchronizing if it's computed by an automaton which is synchronizing and reads output starting with the most significant digit. And symmetrically, I'm going to say that the sequence is backward synchronizing if it's computed by a synchronizing automaton starting with the least significant digit. Now, in cases of forward synchronizing sequences, a result of the Julier-Motta Müllner-Spiegelhofer Shubin-Spiegelhofer asserts that the arithmetical subword complexity is sub-exponential. So it's e to a power that grows more slowly than L. And in fact, they obtained the same result in much greater generality for polynomial subword complexity. And I would say much more about this, but it's been quite thoroughly covered by Clemens 2 weeks ago. So I refer you there. For now, let me just briefly remark that very similar estimates would hold for backward synchronizing sequences, and of course, periodic sequences are nothing to worry about. So somehow, all of the, together with this theorem, we can deal with we can understand the arithmetical subword complexity of the sequences from the previous slide. So we're in good shape if we're uniform, and we're in good shape if we're non-uniform. Now let's see what happens if we somehow combine the two. So here's a very naive example. We can consider a sequence A that's a copy of 2MRs on even integers and copy of twice 2MRs on odd integers. So it's going to look something like this. And now, if we're interested in factors that appear along arithmetic progressions, there are going to be basically two types of those. First, we have factors of 2MRs. Secondly, we have factors of 2 times 2MRs. And then we have factors of 2MRs shuffled with factors of twice 2MRs. And there's two ways in which this could be done. You can start with 2MRs or you can start with twice 2MRs. So at the end of the day, if we just combine all those cases together, we will conclude that the arithmetical subword complexity of A is bounded by some reasonably small multiple of 2 times L. And the key notion that I want to take away from this example is that we started with a sequence that had alphabet with 4 letters, but restricting to arithmetical progressions, we reduced the considerations to just looking at sequences on alphabets of size 2. And this is a more general idea that we're going to exploit, except we need something a little bit more general than an arithmetic progression. I'm going to call those sets k-arithmetic progressions because they are going to also include some information about base k expansions. So these are going to be sets of the form that's an intersection of an arithmetic progression or a residue class if you prefer. But we're also allowed to specify a prefix in base k. We're allowed to specify a suffix, which is a little redundant because you can enforce that by an appropriate congruence condition, but I'm going to keep it for now. And we're also going to include a restriction on the length of the base k expansion, modulus on modulus n. And I'm going to define the effective alphabet size as sort of the least alphabet size that we are going to need to consider if we are allowed to pass to k-arithmetic progressions. So to be more precise, I'm going to say that a sequence A has effective alphabet size R if there exists a k-arithmetic progression P such that whenever I pass to an arithmetic a k-arithmetic subprogression Q of P, then A takes at least R values on Q. And in fact, above this inequality is going to be equality. Right, so let's see this notion in a couple of examples. First of all, if we have a periodic sequence or a synchronizing sequence, then the effective alphabet size is R, is 1, because whenever you have a k-arithmetic progression, you can restrict to a k-arithmetic subprogression where the sequence is constant. In the case of 2MRs, we cannot get any simpler behavior by passing to a k-arithmetic progression, which means that the effective alphabet size is 2. There's also some very basic properties with respect to products and codings. So if we have a product of 2 sequences, then the effective alphabet size of the product is at most the product of effective alphabet sizes. And if we apply a coding to a sequence, then the effective alphabet size can only decrease. So as a consequence of those properties, whenever you have a sequence that's somehow constructed out of periodic forward synchronizing and backward synchronizing, the effective alphabet size is always going to be 1. And finally, perhaps to try and justify this naming convention a little bit more, if you have an automatic sequence with effective alphabet size R, then you can cover all integers with 2 types of k-arithmetic progressions. First, we're going to have some PIs, and on each of the PIs, the sequence takes only R values. And then you have some remainder sets QJs, and the density of the QJs is going to be bounded by epsilon. So if you're willing to accept, if you're willing to erase epsilon proportion of your sequence, then you can split up into k-arithmetic progressions where where you only ever see R different values. Okay, so with this terminology out of the way, I'm able to state our main result, which asserts that if you have any automatic sequence, then the arithmetical subword complexity is grows like the effective alphabet size plus a small error to power n. Now, a couple of quick remarks about this theorem. In fact, in one direction, we have an honest-to-God inequality where the subword complexity grows at least as fast as R to L. And in fact, we can find a family lambda of symbols such that every word over lambda appears along an arithmetic progression. In fact, the same estimate holds for polynomial subword complexity with essentially the same argument. And this value R is computable. So if you have an automatic sequence, you can plug it into a computer and it's going to be able to compute R. So this is a fairly explicit result. And it also has a nice corollary in the case of sequences with maximal subword complexity, by which I mean that the arithmetical subword complexity at L is the size of the alphabet to power L. And for those sequences, not only does each word appear along the arithmetic progression, but each word appears along an arithmetic progression quite often. So the frequency with which it appears is going to be positive. Okay, so that's going to be the main result, whose proof I'm going to try to sketch out. One of the main tools that we're going to use is something that I like to call the arithmetic regularity lemma for automatic sequences. So the statement is going to be along the lines that every sequence can somehow be split up into a structured part and a uniform part. And for this, we're going to need to define what we mean by structure. So I'm going to call a sequence structured if it can be computed as some function f applied to a periodic sequence, a forward synchronizing sequence, and a backward synchronizing sequence. And our result with Kuba and Clemens asserts that each automatic sequence can be decomposed as the sum of the structured part and the uniform part, where the structured part is structured in the sense that I just defined, and the uniform part is uniform in the sense that each Gauer's norm, mu d, tends to 0. In fact, it tends to 0 like a negative power of n. So just to explain why I'm calling this arithmetic regularity lemma, it can be seen as a distant analog of the celebrated arithmetic regularity lemma of Green and Tao. I'm not going to go into all the nitty-gritties of the statement, but it asserts that each sequence, not automatic, not anything, just a totally arbitrary sequence, can be decomposed into a sum of 3 components, so-called nil sequence, a sequence that's small in L2 sense, and a sequence that's Gauer's uniform of order S. Now, if we want to put our statement, our result in the same form, then it's not particularly hard. The periodic sequence we are already quite happy with. The forward synchronizing sequence we can approximate by a periodic sequence plus a small error, and the backward synchronizing sequence we can approximate by a constant sequence on a bounded number of intervals, which means basically that the structured part can be seen as a sum of a one-step nil sequence plus a small error term. So as a result, we can get into the same type of formal expression as above. But the key differences between the two is that in our case, for automatic sequences, you only need to consider one-step nil sequences. You don't need any of the higher order theory. And in the case of automatic sequences, you can, in fact, get very reasonable quantitative bounds when you care about those things. Okay, so coming back to the problem at hand, let me try to relate this arithmetic regularity lemma with the notion of the effective alphabet size. We're going to start with a quick observation that if we have a structured automatic sequence and we have any k-arithmetic progression, then we can always pass to a k-arithmetic subprogression where our sequence is constant. This has a nice consequence that if we have a k-arithmetic progression that takes values, say, in 0, 1, and if, like in the notion of the effective alphabet size, we know that for every k-arithmetic subprogression Q, there's at least one point where A is positive, then we can, then by passing to a k-arithmetic subprogression, we can make we can make it so that the structured part of A is constant and positive. Now, it's immediate from the observation above that we can, that passing to a k-arithmetic progression, we can make A structured constant. So the only reason why this is a lemma and not an immediate observation is that it could, in principle, happen that we pass to a k-arithmetic subprogression and A structured is constant but is 0, which could, in principle, happen, meaning that A of n is non-zero at least once, but very rarely. And then you have to do a little bit of work passing to smaller subprogressions to say that if this was the case, then we would reach a contradiction somewhere. Right, so trying to relate this back to the problem, to the theorem that we're trying to prove. Let's consider an automatic sequence that takes values in some arbitrary alphabet omega, and for x in omega, let me define ax as the sequence that's 0 or 1, depending on whether a is x or not. And another lemma that we're going to use is that if we have an automatic sequence with some effective alphabet size r, then we can find a k-arithmetic progression p and some smaller alphabet lambda, such that ax structured is going to be constant and positive on p for all symbols in lambda. And the proof is just a matter of applying the previous lemma repeatedly. And with this in hand, we are ready to prove the lower bound. So we're aiming to prove that arithmetical subword complexity of A is at least the effective alphabet size to power L. Let's take a k arithmetic progression P and an alphabet lambda, like on the previous slide. And I'm claiming that every word W over lambda is going to appear in A along an arithmetic progression, and in fact, an arithmetic progression that's contained in P. And in fact, I'm going to show that W appears quite often. So let's take some large integer n, and let's try to estimate how often W appears in the relevant arithmetic progressions. So the number of those appearances is just going to be a sum like this. So we sum over all arithmetic progressions, and we have a product of some terms. The first term ensures that this arithmetic progression is contained in P and is contained in the first n integers. And the second term ensures that the W indeed appears in A along this arithmetic progression. Now, generalized von Neumann theorem tells us that at the cost of introducing a small error term, we can replace each appearance of AX with an AX structure. But we constructed P so that all AX structured are constant and positive on P. So this second term is just going to be some product of constant positive factors. And what remains is just the count of arithmetic progressions of the appropriate length contained in P intersected with the initial segment. And this is going to grow like n squared. So this is going to grow much faster than the term introduced by the application of generalized von Neumann. So at the end, the number of appearances of W is positive, and we are done. So that finishes the proof of the lower bound. Now, let me say a couple of words about the upper bound. For this, we're going to need the notion of the height of a substitution. We have an automatic sequence A computed by an automaton A. I'm going to assume that A is primitive, so it's strongly connected, and the greatest common divisor of all the loop lengths is going to be 1. And recall that automatic sequences are exactly codings of k-uniform substitutions. So in fact, let's pretend for now that A is going to just be the fixed point of a substitution, meaning that if you group consecutive k tuples of elements of A, you're going to get the value of the substitution at consecutive terms of A. And the height of the substitution is defined as the largest integer m, which is co-prime to k, and which divides all positions in which A0 appears. And in fact, this is nothing special about 0. You can also have the same definition for any other starting point n. So for instance, the 2m sequence has height 1. Now, the reason why you care about height is that it somehow allows us to extract a periodic part of the sequence. What do I mean by this? Let's consider the equivalence class. Well, let's consider all the symbols that appear in A at positions that are congruent to some fixed j modulo the height. Now, those classes are going to be pairwise disjoint. And if for each element of, for each symbol of the sequence A, we just record in which class it lands, the resulting sequence is going to be periodic. And the height is the largest integer that's comprised to k, such that the above property holds. Now, in a way, the sequence of those equivalence classes Ci is going to contain all the information about the periodic behavior of A that we want to record. And we can somehow use this to extract the periodic component of A. And in fact, for the purposes of exposition, I'm just going to assume, having done this explanation, I'm going to assume that the height is 1, so we don't have to worry about the periodic component. Now there's the matter of extracting the synchronizing component of A. And this is going to be done with the help of a construction that was invented by Clemens in his work on Sarna conjecture for automatic sequences. So let's consider all the sets of states of the following form. We pick a word W and we look at all states that are reachable after reading the input W. And let's consider the smallest possible cardinality of a set like that. Let's call it C. And there's going to be a certain number of sets of such minimal sets. And let's call this family a calligraphic M, and it consists of some minimal sets M1 up to M p minus 1, where p is just some integer. And without loss of generality, I'm going to assume that the initial state S0 belongs to the first of those minimal sets M0. Now, an important property of those sets is that if we have one of those minimal sets M, and if we have any string of symbols U, then if we apply the transition function corresponding to U to all of elements of M, then we again are going to get another minimal set. Indeed, it cannot have more than C elements because the image of a set can have at most as many elements as the set. And in the other direction, it cannot have fewer elements than C because C was minimal. Now let me denote by S of n the state that's reached by our automaton after reading n on input. And let me denote by I of n the index of the set mi, such that if we apply the transition function corresponding to n to m0, we get mi. And this is all set up so that the nth state belongs to the nth minimal set. And this is connected with our previous discussion by the following fact. The effective alphabet size is exactly the same as the maximal number of different outputs produced on those minimal components. And here's a quick sketch of why that should be the case. Well, first let's see why the effective size is at most the size of the output. Well, if we have any k-arithmetic progression P, then by passing to a k-arithmetic subprogression Q, we can ensure that all of the outputs produced by our automaton reading integers from Q is going to be contained in the outputs from at most one of those minimal components. In the other direction, if we just need to show that the effective alphabet size is at least the number of outputs at any given minimal set mi. Now, if we're given mi, we can find a k-arithmetic progression such that whenever we apply our automaton to n in P, then our end state is always going to land in mi, And now the work is in showing that if we then restrict to a k-arithmetic subprogression Q, then we can still reach all states in MI. And this is a little work, but it's not terribly hard. So now with this in hand, we're able to finish the argument. So because the output at n is definitely going to lie in the in tau of m of I of n, the number of subwords that we see along an arithmetic progression in our sequence A is at most, well, the number of possible choices, which is at most R to the L, times the number of possible patterns of those minimal sets that we're going to see. And this is the same as the arithmetical subword complexity of the sequence I that I introduced on the previous slide. Now the sequence I is k-automatic and synchronizing, so we're able to apply to it the result from the previous talk to say that the arithmetical subword complexity is sub-exponential, and combining the two, we immediately get the claim. Now a couple of quick remarks. There were a couple of simplifying assumptions along the way, so this is not quite a complete argument, but it's relatively close to the complete argument. There's not that many more technical details, so it's a really short paper. The same results apply to polynomial subword complexity with essentially the same argument, and you can be a little bit more careful with the sub-exponential error term, and you can put it in a form like on this slide. And I'm a little over time, so I'm going to end here. And thank you so much for your attention.
Thank you so much, Jakub. Does anyone have any questions?
Yes, I would like to ask, in fact.
Okay.
Do you have any more or less precise examples of the complexity values, other than either exponential or linear growth? Do you have, if there is, do you know if there is any variety more than that?
Oh, I do not know. I only looked at. I was only investigating this in the case of automatic sequences. In the case of automatic sequences,
sure. I mean,
we always get exponential.
I mean automatic sequences, because we have examples of linear arithmetic complexity. We have examples of exponential.
Right. And
do you see anything in between?
Oh, no, it follows from the theorem that there is nothing in between. The complexity is always of this form. So it's always going to be.
I see.
Oh, sorry. Okay. So it's going to be either exponential, or it's going to be of the form 1 plus little o of 1 to power l, which yes, sorry, it could be quite arbitrary in between.
Well, we know that there are linear examples, so
yes. And
my question, do you know if there is something quadratic, for example?
Oh, no, we do not know. In fact, for a time we were thinking that perhaps we can prove linear, but this would be quite difficult. This basically boils down to where was this? So this would boil down to improving this theorem of the five author paper, and as far as I'm aware, this looks like a pretty difficult problem, and we do not have any examples. We do not know.
Okay, thank you.
Sure. Sorry, I couldn't be more informative.
Thank
Are
you.
there any other questions? Dan.
Hi, yeah, thank you for the great talk. I was just wondering the structured decomposition result that you had. It reminded me of the Abelline decomposition of a measure. Do you know if there's a relation there?
I do not know if there's an explicit relation. It's definitely an interesting question, but I do not know the answer.
Okay. Yeah, I mean the people looking at like spectral decomposition of these sequences use the Abelline decomposition all the time, and it's very similar, so it might be worth looking into.
Yes, I will definitely have a closer look. I'm not terribly familiar with Abelline decomposition to be quite honest, but it definitely sounds like something that could be related.
Okay, thanks.
Thank you.
Are there any other questions? All right. If not, thank you again, Jakub.
Well, thank you very much.